So without further ado, please join me in giving a huge welcome to Bruno from N26. Woo! Yeah, that's right. Yeah, I hear you at the back, right? Woo! Woo! All righty.
Yeah, so I'm here to talk about JavaScript, right? Surprise, surprise, no web conference. But I want to take you in a journey with me, so I want to peer behind the curtains and actually show you how interpreted languages work, right? Like, you probably have heard about Python, Ruby, all those amazing languages, by the way, and they all work in a similar fashion. JavaScript is no different. There are a few components that we'll talk about them very soon, and hopefully it's going to be fun. So yeah, a little bit about me. My name is Bruno. I'm a tech lead at N26. I'm currently working in the platform engineering team. We're basically building tooling, for the web engineers to actually build the product. It is pretty interesting to me. I'm really deep into monorepos, CI pipelines, infrastructure for web, and so on. I'm not a front-end guy, but I really love React. So yeah, don't judge me by my front-end skills. You're going to see it at the demo. But hopefully it looks good enough. Yeah, I'm a software engineer by trade. I have been working as a software engineer for the past 14, 15 years. I'm originally from Brazil, but I have been based in Vienna for the past 8 years. I'm soon moving to Barcelona, so this slide is going to change slightly. I'm also a big fan of programming languages in general. I try to learn new languages every so often. I'm really into Elixir now and Rust. But I'm also a big fan of web technology, right? The browser, it's an amazing thing. I mean, I was watching the other talks about React Native. I was really impressed. I didn't know React Native was in such a really cool state. I had no idea. I really needed to look into it because it's really amazing. But the coolest thing is that the technology that powers React Native, it's also powering the browser, right? And all those really cool platforms that you see out there. I'm going to talk about this a little bit. I'm on Twitter. This QR code should lead you to my profile. I'm also on GitHub. My DMs are open. I'm happy to chat. I'll also be around here the whole day. So I'm happy to grab a coffee and then have a chat later. But before we start, did you know that the console object is not part of JavaScript? So this little object that you use every day and love, it's not really part of the language. But somehow you manage to use it, right? But it's actually a gift from the runtime. So you use it every day, but the language doesn't have it. It's because this is not a part of the spec or the ECMAScript spec, but it's part of the runtime. We're going to see those two components together. And this is a little agenda for today. So I want to take you in this little journey coming all the way from your source code, right? Like you start writing those blobs of text in this index.js files. And then somehow, like magic, it just happens to show on your screen and do computations and so on. But I'm a guy that I don't really enjoy magic so much, so I want to actually see what's going on behind the scenes. So I want to take you in a little side quest. So I want to talk about the JavaScript engines and runtimes a little bit, so you have a better understanding on how those things work. Then we jump in, we come back to the main quest of our journey here, and then we talk about tokens, lexers, tokenizers. Some people call them scanners as well, and why they are so important, so helpful. Then we jump into the parser phase, which is actually like one of the most interesting parts to me. Is that's where you actually build your abstract syntax tree. If you haven't been dealing with abstract syntax trees on a day-to-day basis, that's fine. You're usually not doing that often. Generally, you're doing that when you're dealing with tooling. But that's basically what's happening with your code at the end of the day. Then you jump into the interpreters, and this is the guy that actually makes the magic happen in a sense. So it takes out your syntax tree, and then it magically, resolves all the nodes, and then make the magic happen at the end, and then show pixels on the screen, or make a database call, and so on and so forth. Then at the end, I have a little live demo to show to you. I mean, my plan was to actually build the whole tokenizer, parser, interpreter during the talk, but just half an hour, it's tough. And I'm also getting hungry, so that would be quite a task. Okay, so let's just start with a plain JavaScript file, right? You start your journey by writing your program like this, right? You write your JavaScript there, very simple statement there, let result equals to 1. But let's see what actually Chrome does to actually make this a reality, right? You're binding a value to a variable, right? But how does that work? Chrome has this incredible piece of software called V8, And this is really what makes your JavaScript so fast in the browser. It's really fantastic. And those are the steps that V8 takes. And a rough picture, I mean, it does a lot more than this, but this is basically the big picture. And it started from the top. V8 in the browser, fetches your JavaScript file from a remote server, from your HTML page. And then it shoves it to the parser. So the parser, analyzes your text, basically a stream of text. And then it transforms it in this abstract syntax tree, right? This is a representation of your program at the end. But this is not executed yet. It's just like this picture of your program and what this could look like when it runs. And then when the syntax tree is ready, then this is passed down to the interpreter. In V8, this is called Ignition. It's its own little software inside of V8. It's really incredible. And this is the guy that's analyzing the syntax tree and then processing your code, basically, not line by line at this stage anymore, but basically node by node. But V8 implements a very neat architecture where it not only compiles down to bytecode to execute it faster, but also if it detects that your JavaScript is running like that specific function that's really like running several times a second, it detects it as a hot path, and then it sends this portion of your JavaScript program to TurboFan. TurboFan is this just-in-time compiler, so it takes your portion of the syntax tree, and then it compiles down to machine code, and then it makes it even faster. Sometimes this doesn't work as well. Like it can actually be slower than the bytecode. So TurboFan is analyzing the metadata, basically the metrics of this running code. And then if it turns out that's not really performant, it sends it back to Ignition, and then Ignition continues to execute the bytecode. But this is just half of the picture, right? Where do you see, when you're working in the browser, where do you see your window object, right? Like where's the console object there? This is because the browser and many other environments, they are actually composed by mainly two pieces, right? You have the JavaScript engine on one side, and then on the other side you have the runtime. And the console object actually comes from the runtime. I have two runtimes here, which is the browser and then Node.js. In the browser you can see the console object, the window object, timers, event loop, the DOM API, all the web APIs, right? This is the runtime binding those objects into the engine and then make it available to you. In Node, you have different APIs, right? You have file system calls, you're doing sockets, you're doing HTTP calls. You also have the event loop there, callback queue. And by the way, the event loop is not a Node.js thing. It's actually a pattern. It's also implemented in different languages. For example, in Rust, there's this famous library called Tokyo, which is the async runtime. It also implements a event loop there, basically. So this is a pattern that's implemented everywhere. And in Node.js, for example, you have this library called libuv. You see this little dinosaur with a bit of a unicorn there. libuv is the library that makes the magic happen between different operation systems. For example, imagine you're doing a file system call, or you're reading a file, and you need to read this file on Windows, Linux, and Mac, right? Imagine that you have to write 3 different APIs for doing that. So the folks from the Node.js who wrote this library to kind of like abstract this away, and then the JavaScript APIs can call in. And libuv is so good and so popular that's been used by other programs too. Like I think Neovin also uses it. There's a bunch of other software that uses libuv as this foundational layer to provide this API on the operation system. But this is interesting to me because that's why you see so many companies improving their runtimes, right? Like you see them investing a lot of money and time and effort on creating new runtimes. For example, Bun is doing that in Zig. They're not using V8, they're using JavaScript Core, which is the engine from Apple. Deno is writing their runtime in Rust, but also using V8 as the engine. And then the Cloudflare folks are also doing a runtime as well with different APIs, right? You have all those edge APIs. But they don't want to reinvent the engine. The engine is doing its job really fantastically well. And you just want to piggyback on it and then make sure that you can just reuse it. And that's the main difference between the engine and the runtime. But let's come back to our main quest, because I want to focus on this here. We only have half an hour, so I have to be quick. We want to focus on those 4 boxes at the top. I'm not gonna go into detail on the other ones, but hopefully we can cover those pretty quickly. So I want to focus on fetching the file, passing, generating the AST, and then interpreting at the end. But at the end of the talk, we're gonna see a demo that everything that you see in those boxes I have implemented only using the JavaScript standard library, and basically powers this whole thing. So yeah, let's go back to our first example here. Start with your JavaScript file. You have your stream of text, but they don't mean much, right? It's just plain text at this point. And that's where the lexical analysis come into play here, because it basically does this phase where it analyzes your string, like string by string or character by character, and then it tries to make sense of them, And the way it does is basically like, okay, you have a language. This language has specific keywords, right? Some of them are reserved. You have to use them for certain constructs. Some of them you don't have that in the language. Like for example, result is just a name of the variable, right? It could be anything. But you have also symbols like equals, the number 1 is a literal value. And at this step, you just try to classify your tokens. You put them in boxes and then you tell, hey, this is a literal value, this is a string, this is an operator. In this phase is important because, it gives us a lot of metadata. For example, location information. Think about when you're programming and then you have a stack trace that points to, there's a crash here on line 45, column 57. This is where it comes from. This phase embeds this metadata, and then it can actually give you more information as a program language designer on how to actually show error messages. If you think about programming languages, the user interface of a programming language is usually just text, right? You're giving back feedback to the user just as text. Basically with compiler errors, syntax errors, and so on and so forth. So you have to be very good at analyzing text, basically. You also have literal values. For example, the number 1 there, it's literally the number 1. You don't have to evaluate this at runtime. At runtime, you have the value there, so you can just use it. And that's a lot faster than trying to evaluate it. So you store this information too. But you don't have syntax context there. So at this phase, I'm just trying to classify those tokens in a way that they have those little boxes. But you can tell whether there is a syntax error here. At this phase, it's not like really concerned about telling, hey, there is a mistake here. You have to fix it. This is the job of the parser. We're going to see it later. But this is already very useful. Think about like if you're working on tooling, and then you want to write like a syntax highlighter, for example. If you manage to get to the phase where you're doing lexical analysis, you can already write like a VS Code extension, that highlights your programming language, for example. That would be possible already at this stage with the output of this stage, which is just this list of tokens and then this classification of them. But let's take a step back and then let's have a look at this different example here. Who can tell me what is the value of this expression? 8, yeah, that's right. But why it's 8? Yes, that's right. You start the multiplication, right? And then you do the sum at the end, right? But how the heck does the computer know how to do this? I mean, you know this because you know the rules that apply here, but the computer doesn't have any clue about this, right? Like there must be a way to tell it on how to do it. And there's no magic here. Like it can't know it like implicitly, right? If we look again at this same example, now I'm just wrapping them in parentheses. This makes more sense, right? I mean, if you look at it, you can tell, okay, the multiplication maybe should come first because it's a group, and then it should be resolved from the inside out, so on. But if you look closer, does this line represent some sort of data structure that can tell you this? I mean, who can take a guess what this looks like? Basically a tree. So you can represent that as a tree where those nodes are connected somehow, and then they have meaning that you have to resolve them in some way. Like for example, in this tree here, you see the bottom of the tree should be the ones that are resolved first, and then it walks back all the way to the top. So let's walk through this tree. We have done this already, but now in the tree form, you have the same tree that we saw in the slide before. Now you do the multiplication first, right? Now you have 6 plus 1 plus whatever comes after. Then you have 7 plus 1, and then you have 8. Right, that's the result here. But how can you build this tree, right? Like you have to codify this somehow, so then this tree comes out. I mean, it can come out from nowhere, right? You have to apply rules to it. And this is where formal grammars come in. I mean, if you're into languages, let's say the English language, you have a formal grammar, right? You have a way of writing sentences. They have like a limited set of amount of rules, but you can produce infinite amount of phrases with it, right? And it's the same way for programming languages. You basically build up this formal grammar, those rules, whatever they are, and then you apply it, and then you can generate an infinite amount of programs, right? That's basically what we have been doing here every day. We're just applying this grammar. You know this grammar by heart. You just don't know how this is defined, maybe. But a grammar is this finite set of rules, but it can produce an infinite amount of strings. And this is divided in simple definitions. Like we call them productions. So each rule is a production. And then this production is defined with a head, which describes the rule, and then the body. The body is basically how you can actually resolve that rule. And the bodies are composed by terminals and non-terminals. Terminals are basically like, okay, if you got here, that's the last stop. If you go to a non-terminal, you have to resolve it back to a different rule. So it's kind of like a recursive data structure in a sense. And this is how you represent grammars. You don't have to be worried about like understanding how this whole thing works. But the gist here is that those rules, they have to follow a certain order, and then they have to obey this, the sequence that it comes from the grammar. For example, you start with an expression. The expression can resolve to a term can resolve to a factor can resolve to a primary to a number, and then back to expression again. So it's kind of like a recursive data structure again. But this is the grammar that makes this kind of tree possible. This is the one already for this specific tree. And we will see that in code very soon, how you can actually codify this. You see that there's a bunch of symbols there. The ones that are in quotes are actual symbols that should show up in your code. And then the terms in black are basically rules. So you have to resolve them. Don't worry about it. I mean, if it's confusing, we'll see that in action very soon. But this is what we call a recursive descent parser. So if you see this fancy term for a parser name, that's basically what this guy is doing. It's really a fancy term for a very straightforward recursive function. You have this big recursive function that's just walking through those rules and then resolving them one by one. It takes the list of tokens that we saw before, and then it transforms this in the syntax tree based on those rules that we defined. And it just starts from the top and then goes all the way to the leaves. That's why it's called a recursive descent, because it goes in a descent order. And if you want to visualize that syntax tree that we just saw before, for that little example that I showed you before, it should represent something like this. You have a binary expression that has like a left side operator and then the right side. And then on the left side itself, you have another binary expression. So you see the recursive element of this, right? And then you also resolve it to operator, left and right. If you really want to explore how this works, there's this really cool website called AST Explorer. You can just type it in any JavaScript code there. And then you can basically see the output of the syntax tree there. This is the representation of your program. That's what V8 is doing, for example, before executing your program. And this is super helpful because if you get to this stage where you actually have a AST, think about your building tooling and you want to refactor a really big code base that has like anonymous function, and suddenly you want to come up with new names, or you want to rename a specific function across the code base. And suddenly, if you just do like a regex pattern, you might screw up some bits of the code base because maybe you have this reference in a different way with a different name. But if you manage to actually get a AST out of it, you have all those references already built up, and then you can run like a lot more powerful tooling on top to do refactoring. This is really cool. There's many libraries that already gives you the AST. But it's important for you to understand how AST works, right? So then you can actually apply those rules yourself. And once you have the AST, you're pretty much like ready to execute a program. You have this representation, but nothing happens yet. And that's where you get to this stage of the interpreter. So the interpreter, it's actually the one that just walks through this tree, walk through it every single node, and just evaluates them. We did that before, right? A couple of slides before, we saw the tree, we just resolved them, and then we got to a result. It's the same thing that you have to do in an interpreter. Basically, Ignition is doing that in V8 in a different form, of course. And this is where you can bridge the gap from, from your custom programming language or from JavaScript itself to different programming languages runtimes. Like, for example, in Node.js, Node.js is written in C++ together with JavaScript. But Deno is in Rust, and then Bun is also in Zig. So those are the runtimes that are allowing you to write JavaScript, and transition those objects back to the runtime that's actually running like native code and so on. That's why JavaScript is so fast, because at the end of the day, you're running native code, but there's a lot of time that's spent analyzing your code, right? Like we saw it in V8. And this is called the tree walker interpreter. Basically, very straightforward, right? Like you do a walk across the tree and then you resolve this. And this is the interpreter that I want to show you guys now in the demo. But before we move on to the demo, I think we still have enough time. Yes. I want to recommend those 2 books. Those books are really fantastic if you're interested in learning about this stuff more deeply. Crafting Interpreters is a perfect book. None of them use JavaScript as a base language. Crafting Interpreters using Java in the first part of the book, then C to build out a compiler. Write Interpreting Go is Go, but it's really easy to follow along. Even if you don't know Java or C or Go, you should be able to follow along just fine. Highly recommend this book, even though if you're not planning to work on programming languages, tooling, all that stuff. But it's really good to understand how those things work. One thing that I advise to engineers working with me is like, always go down at least 1 or 2 levels deeper than the tooling that you work on a day-to-day. That's going to make you a much better engineer at the end of the day. Cool, so this is time for the live demo. I have this little QR code there you can scan. I'm going to put these slides online as well. But this is all on GitHub. And then you can build yourself and check it out. So let's see. Let's take a look. This is the app that I built. I know it's not super fancy, but let me explain what's going on here. On the left side, I have this text area that's taking the expressions. So you can write whatever expression that you want. I took the one from the example before. On the right side, we have the result of the interpreter, basically, doing the stuff that we saw in the slides before. Below it, we have an eval as a sanity check. Eval is how you can evaluate JavaScript in JavaScript, but don't do this at home. It's really dangerous. And then below it, we have an AST explorer. Like I built a very minimal version of the website that I told you before, just to show you the AST that pops out from this. So if I type in more expressions here, we should see the results coming up quickly. I can also wrap stuff in parentheses here. And then, okay, let's see, +2. Then hopefully this is right. And then the AST comes out of it, and then you can analyze this. But how does this work, right? Let's take a look at the code base here. So I have a plain JavaScript project here, just using React. There's no libraries here. So if you look at the package.json file, there's only React and React DOM. I'm using Vite to build out the app, but nothing else. If you look at the app.js file here, you should see one use effect here that's managing all the steps that I showed you before. We have the tokenizing phase or the lexical analysis phase that actually gives me those tokens. Then we go to the parser, and at the parser level, I pass those tokens down to the parser, and then I tell you to pass those tokens, give me back the AST. Once I get the AST back, I just shove this guy into the interpreter. The interpreter interprets this AST, and then gives me the result, and then I show it here. Pretty much like very straightforward. But let's look how this actually works. So let's take a look at the lexer first, because that's the first step in the parser phase. So the lexer, it's really not doing much. It's a while loop, and then it's just walking through the input that I gave, basically like a big string, just walking through character by character, and then just trying to analyze and make sense of them. So I call this function here. So if it's not at the end, I call scan token. So it should go, oh, come on. Should go to scan token. In the scan token, I have this huge switch statement here, and it's just looking up each one of them, right? So there's nothing fancy here. It's really just adding tokens to this array. There's like a little helper function here that passes those tokens in certain way. For example, for numbers, I can actually support floating point numbers. So this is how I'm actually supporting them in the input. For example, if I see a dot there, okay, it might be a float pointing number. Let's look at the other half that comes around. So if I go back to my browser here and I do 2.5, it should work too, right? So this is also handling it. And then it just shoves it back to this list of tokens. So let's take a look at the token implementation. It's pretty much a simple class. It could even be just a plain object, to be honest. I just kept it as a class, so it's consistent. But it's just stores, the kind of box this token belongs. It's a kind. There's a lexeme. Lexeme is the representation of that token. For example, the plus sign is the representation of the plus operation. And then we have the literal value. In this case, like could be 1, could be 10, could be a string, and so on. Then let's take a look at the parser now, because now that we have this list, we can take a look at the parser. And here we see that grammar again that we saw before. At the top, I just define the grammar here as a comment. And then I just try to implement that in my parser class. And what this guy is doing. So you see, it starts with an expression, then it falls back to a term. A term tries to resolve a factor. Then it tries to resolve a power, and then a primary, and so on. So let's look at this here. The constructor takes a list of tokens. We already built this. And now we start the parser phase. The parser starts from the first grammar rule, which is an expression. So if you come here, the expression just tries to resolve a term. And then a term tries to resolve a factor. If there isn't a factor there, then we do a while loop and then check to see if a plus or a minus, because the factor tries to resolve those first. And then if there is one of those symbols, and then it tries to resolve the right side and left side. And that's where a lot of recursion come in handy here, because it goes back to factor again, it goes down to factor here. And then factor tries to do the same thing, but for slash operations and star operations, right? Division and multiplication. But notice the order here as well. So this is where you can codify the order of the rules, because it's coming after. So everything that's coming after, it becomes a node down the tree. And it also tries now to do a primary, and then a primary is either a literal value, which just resolves to a number. I'm calling this a literal. I also have like little wrappers to hold the state. Or if it's a grouping, it goes all the way back to expression. And then we start the recursive function again. You see, like, there's a lot of recursion here. It could be a little complicated to wrap your head around it, but it's very straightforward. Once you build up this tree, that's basically what we see here in the ST Explorer, you're ready to execute this. So you got the representation of your tree. Now you want to execute that. And that's where the interpreter comes in. And then here, it's basically a big switch. Again, you're just like evaluating each node. And then depending on what they tell you, you just evaluate them in a certain way. For example, if I start evaluating my expression here, and if this guy is a literal value, let's look at literal value. It's literally returning the value to you back, nothing else. So if it's a number 1, just return the number 1. If we look at the grouping, or maybe this is not so interesting. Let's look at the binary, for example. If it's a binary expression, then a binary expression is composed by a left side operator and then the right side, right? So I just grab them, resolve left here, resolve right. Them on itself, they could also be recursive. That's why I call evaluate here, and then I pass the node, because this should start my recursive tree again, and then walk the nodes back again. But if you see at the end here, depending on the operation, this is plain JavaScript, right? Like I'm doing now left minus right, left division right, left multiplication right. So this is how the interpreter works. This is This is what, for example, V8 and runtime is doing behind the scenes. It's just doing this execution in the C++ layer that's doing this for us, basically. At the end of the day, it's translating to this in the native language. And once you have this, then you basically come back here, and then you have a result, right? That's the stuff that we saw on the screen. So yeah, this is the end of my talk, and hopefully I gave you like some interesting toolies for lookup and then learn more a little bit about this. I'm pretty sure with those basics here, you can actually go and build up your programming language, because of course this is very basic and it's just very the beginning of everything. But this is not super far away from defining functions, variables, closures, classes, and all that stuff. That's like fascinating to me. And you're definitely armed now to do that by yourself. Thank you so much.